Lesson 9.5, Classes of Functions. And we're going to take a look at the terminologies that describes parent functions. The first one is constant function. And we ask ourselves, why would they call it constant? And the intuitiveness would say, well, constant means it never changes, and what kind of line looks the same all the time? And that would be a horizontal line. So that's an example of a constant function. A direct variation equation, where we talked about y equals kx, and looking at that, notice that the slope can be anything, but the y-intercept is always 0. So two characteristics are that it goes to the origin and it is a straight line. Identity function. Well, identity would mean yourself, okay? Knowing who you are, knowing what, if you look in the mirror, you see yourself. So an identity function would be something where if I had a coordinate 1 for x, then the y would be the same, or 2 and 2. So all the points would have the same value in terms with respect to identity. So that would be a diagonal line. So we have all the points there. We have 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2, and so on. Identity function. Greatest integer function was done a while ago. This is a non-continuous function because it breaks up. You have to pick your pencil up and you graph it. This is step function. There's another name for it. For obvious reasons, it looks like steps. So if an equation includes an expression inside the greatest integer symbol, this function is a greatest integer function. Okay, so if it's a decimal, in this case, it's a double-stemmed a double-stemmed bracket. In this book, some books have different notations. This is an example in this one. And this is a floor function, which means whatever goes in it takes it down to the nearest lowest integer. Okay, so if you get 0.5, it takes it to a 0. If you get 1.5, it takes it down to a 1. If you get 1.1, it takes you to a 1. So no matter what it is, it rounds it down to the next lowest integer. If it's 2, it stays at 2. So it takes all the decimals and takes it down, ignoring all proper rounding rules. Okay, so 6.9 still rounds down to 6. Absolute value we've seen before. This is an example of the absolute value, where 0, 0, then 1, 1, 2, 2. Plug in a negative 1, it makes it positive. Negative 2 makes it positive, positive 2. Quadratic function, we've seen a lot of this. It's a parabola, it has a vertex, a lot of symmetry, and so on. All parent functions. Now these are some new ones. A square root function. Well, you cannot have a square root of a negative number, so keep that in mind. It would involve imaginary numbers. So at 0, 0, square of 0, 0, it does not go to the left. There is nothing here because you cannot take the. You can take the square root of a negative 1, but it's going to give you an unreal solution. So it stops on this graph. And then you just take the square root of 1, you get 1. Square root of 2, square root of 3, square root of 4 is 2. But it slowly planes out. Rational functions. Talked about this, where you have a polynomial in the numerator and the denominator. Inverse, where we talked about 1 over x, where we had direct variation was 1 equals kx. This is, or excuse me, y equals kx. Here it's y equals k over x. In this case, k is 1. We talked about this the other day. If we have a rational function and the denominator cancels out and you simplify, it becomes a whole. And sometimes the rational function becomes linear. So this is an example of one of those where you had something that might have looked like this when it was factored. So it's undefined at a certain point at 2, and then we cancel out those two pieces, and now it's linear. Y equals x plus 1. But there would be a hole at 2. So that's an example of what that could look like. Alright, so in looking at these two examples, what are we looking at? This stops, and it gradually increases like that. This is a square root function. This one we just talked about it. There's a hole in it. So a rational function. Okay. Now here's an example of a word problem for science. You have a rocket ship that takes off. With this equation, which one of these pictures represents the flight of the rocket? The answer would be B. They're starting at the ground, so it starts here, the rocket ship goes up, and comes back down after so many seconds. So this would not work there. The rocket ship does not continue and go across the sky as constant, increasingly more and more constant height, so that's not going to work either. And again, here they start at 80, and they told us they started at ground level. All right, identify the type of function, you graph it. Well, because of the absolute values, we know it's an absolute value equation, so it looks like that. So how does this affect it? It's supposed to be here, but that -3 shifts it down 3 units. So there's the parent function affected by a vertical shift. Next one. All right, well, we see the root, so that's a big clue. Must be a root function. Square root function. If you remember, that one looks like this. But you have this to think about, so it must have shifted it down too. But what does this do? If you graph it on a graphing calculator, it's going to stretch it higher sooner. Okay, so here's what we got. I don't have any points graphs. This is definitely an approximation, but it gets higher quicker as it goes to the right. All right, this one. Well, rational function. We notice the top is factorable though. So we get x minus 3, x plus 3 over x plus 3, which allows us to cancel the x plus 3's out. So you get y equals x minus 3, which means it was undefined at -3, but it canceled out. So this could have been an asymptote, but now it is a hole. So now we would graph this. Y-intercept is -3. Slope is 1. And as this goes down, at -3, okay, you go down to where it hits your line. We have a hole. And that's how we represent that rational function. All right, and that ends lesson 9.5.